Hola, bienvenidos a mi charla. Hello, welcome to my talk. My name is Alexander Barrios, and today I have the great pleasure of sharing my research with you as part of the Lathisms lecture series. Before we begin, I would like to extend my thanks to Dr. Pamela Harris and the Lathism staff for their invitation. Today I will be talking about two topics that are very dear to me, namely the ABC Conjecture and elliptic curves, and in many ways my primary research interest over the last several years has been influenced by my desire to understand the ABC Conjecture in the realm of elliptic curves. Specifically, what I mean by this is that, as we will see, the ABC Conjecture is equivalent to what is known as the modified Szpiro Conjecture, which is a statement that pertains to elliptic curves. And so with that, let's go ahead and give an outline for how the talk will progress. We'll begin with a brief discussion of Formosas Theorem, and then transition to the ABC Conjecture, its statement, and we will also see how in its explicit form we can actually recover Formosas Theorem for exponent n greater than 5. We will also see some other consequences of the ABC Conjecture, and after that we'll progress towards elliptic curves and define what we mean by an elliptic curve. And I should note that as part of this talk I am not assuming any familiarity with these concepts until the necessary background and language will be introduced. Once we have defined the background on elliptic curves, we'll move towards the modified Szpiro Conjecture, which is the equivalent formulation of the ABC Conjecture in this realm. We'll talk about some results that we can get in translating what we know pertain to the ABC Conjecture, but now viewing it from the perspective of elliptic curves. And finally, we'll conclude with some of the ideas of how the proofs discussed in section 4 come about, namely by studying what are known as modular curves that allow us to parameterize elliptic curves with certain structure. So, to discuss Formosas Theorem, we begin with the Pythagorean Theorem, which actually dates back over a millennia to ancient Babylon. And what it tells us is, of course, if we have integers a, b, and c denoting the sides of a right triangle, specifically a, b, and c are positive, and we let c denote the hypotenuse, then of course a squared plus b squared is equal to c squared. And we could ask, are there positive integer solutions to the Pythagorean theorem? And of course we have a plethora of examples that we have grown up with. So 3 squared plus 4 squared equals 5 squared, and various others. But are there infinitely many? And the answer is yes. And this goes back to Diophantus of Alexandria, who in 250 of the Common Era wrote what is known as the Arithmetica. And while some of the books that compose the Arithmetica have been lost, what we do know is that he did prove this result, and the proof is in the Arithmetica. And what it tells us is a complete classification of how every single Pythagorean triple looks like. And so, well, specifically Pythagorean triples that are relatively prime. So we want to avoid things like 6 squared plus 8 squared equals 10 squared, since 6 and 8 are not relatively prime. And so what Diophantus tells us is that if a, b, and c are relatively prime positive integers, then a squared plus b squared equals c squared if and only if there are relatively prime positive integers p and q of opposite parity, so one is even, the other is odd, such that p is greater than q, and we have that the following equations hold, although we may have to interchange a or b depending on whether one of them is even. And so we'll take a to be the even one, and that will be equal to 2 times p times q, b is equal to p squared minus q squared, and c is equal to p squared plus q squared. Now, we can reinterpret Diophantus' result in modern terminology and actually have a parameterization of all such Pythagorean triples. So to this end, let us suppose that we have real numbers a sub I, b sub I, c sub I for I equals 1 and 2. And let tilde be the relation on R3 given as follows. We're going to say that a1, b1, c1 is related to a2, b2, c2 if and only if there is some non-zero real number lambda, such that a1, b1, c1 is a scalar multiple of a2, b2, c2 by that lambda. So specifically lambda times a2, comma lambda b2, comma lambda c2 is equal to a1, b1, c1. It turns out that this tilde is an equivalence relation on R3, and what we are going to do is denote the equivalence classes with respect to this equivalence relation by a1 colon b1 colon c1. And from this point of view, then we have that 3/4, 1, colon 5/4 that equivalence class is the same as 3, 4, 5, since all we have to do is scale each of the entries here by 4. And doing so gives us 3, 4, 5, our Pythagorean, which we can know 3 squared plus 4 squared equals 5 squared. Another example, we can start off with 5 ninths, colon 4 thirds, colon 13 ninths, and then scale all of these entries by 9, and we get 5, 12, 13, which is another Pythagorean triple. And let's do one more. If we start off with 16 over 25, 6 fifths, 34 over 25, then we can go ahead and scale this by 25 over 2, and we will get 8, 15, 17, which is another Pythagorean triple. And the reason for these numbers, the way that they're chosen, is that we get the following equivalent formulation of Diophantus's result in this language. But now we can drop the relativity primeness in Diophantus's original statement, because 3, 4, 5 will be equivalent to 6, 8, 10, which is the Pythagorean triple I alluded to, where 6 and 8 are not relatively prime. And so what the reformulation tells us is that if we have integers a, b, and c, then a squared plus b squared equals c squared, if and only if there is some rational number t, such that ABC, the equivalence class of it, is equal to the equivalence class of 1 minus t squared, colon 2t, colon 1 plus t squared. If you haven't seen this result before and you're curious on how one proves this, the way you go about this is by considering a squared plus b squared equals c squared. If we divide by c squared on both sides, we're going to have a over c, quantity squared, b over c, quantity squared, equals 1, but this is just a solution to the unit circle. X squared plus y squared is equal to 1. And so after that, with that in mind, we can look at a circle. So here's our circle, here's 1, 0, and then we can consider the following. We can consider a line that passes through 1, 0, but importantly, this line has slope t. And so the slope of this line will be equal to t. And now the point slope formula tells us that the point of intersection with the circle right here must be a rational point. And so these quantities here can be attained by solving for the intersection of a line with slope t passing through 1, 0 and another point on the unit circle. But importantly, as we go towards discussing modular curves later on, what I want you to think about with Diophantus's result in this formulation is that we are parametrizing all Pythagorean triples by rational numbers. And so a rational number t will correspond to this equivalence class, which then gives us all the Pythagorean triples that can be scaled from 1, from that specific t. So let's fast forward to 1621. So Claude Gaspard Bachet wrote a translation of the surviving books of the Arithmetica in 1621, translating it from Greek to Latin. And in 1636, a French lawyer by the name of Pierre de Fermat bought a copy of Bachet's translation of the Arithmetica. And in the same exact theorem that we just saw pertaining to all the Pythagorean triples, Fermat asks, well, what happens if we have a to the n plus b to the n equals c to the n for n greater than 2? Do we have integer solutions? And he famously stated that there are none. And so this was written as in the margins of the same exact theorem of Diophantus that we just discussed. And so he mentions that he has truly discovered a truly marvelous proof of this, which this margin is too narrow to contain. And so this result came to be known as Formosas Theorem, and it tells us that if a, b, and c are integers such that a to the n plus b to the n equals c to the n for n greater than 2, then the product of a, b, c must be 0. Now, Fermat wrote another 47 marginal notes in his copy of the Arithmetica, and some of the other marginal notes that he had were claims that he had proven various statements, and only one of them he actually proved, at least that we know of in terms of his writings that survived. And so that is the right triangle theorem, which tells us that the area of a right triangle with integer sides cannot be a perfect square. So this is the only result that we know that Fermat actually had a proof for. But other results that Fermat claimed to have proven are what is known as Fermat's little theorem, which tells us that if we have some prime number p and some integer a that is not divisible by p, then p will always divide a to the p minus 1 minus 1. So this was first proven by Leibniz in 1683, but Euler will be the first one to publish a proof in 1736. Another result of Fermat that he wrote down and claimed to have proven is the sum of squares theorem, which tells us that if we have some odd prime p, then p is equal to a squared plus b squared for some integers a and b, if and only if when we divide the prime by 4, its remainder is 1. Equivalently, p is congruent to 1 modulo 4. And so Euler dedicated a good chunk of his professional career to proving the 48 marginal notes that Fermat had listed. And so the reason for calling Fermat's last theorem the last theorem is that it was the last of the 48 marginal notes that remained open going into the 1800s. So let's go towards 1955. And so here I'm going to introduce some terminology and we'll come back to what these concepts mean when we discuss elliptic curves. But the main thing is, in 1955, two Japanese mathematicians, Taniyama and Goro Shimura, made a deep conjecture relating to branches of mathematics, elliptic curves and modular forms. In 1981, Lucian Szpiro formulated a conjecture relating the minimal discriminant of rational elliptic curves with their conductor. And the key between Taniyama Shimura and Formosas Theorem comes from Gerhard Frey, who in 1982, by considering the conjecture of Szpiro from 81 and work that Hellegorch had done on what is known today the Frey curve, Frey realized that if Formosas theorem is false, then one can contradict the Szpiro conjecture. But then he went on further to study the properties of such counterexamples. And this led him to make the following deep observation, that if the Taniyama-Shimura conjecture is true, then it would imply Formosas theorem. But Frey gave a roadmap with the pieces were eventually filled in by other mathematicians, most notably Jean-Pierre Serre, Ken Rivett, who I'll talk about in a moment. But in 1985, the Szpiro conjecture also motivated another conjecture, which is the one we're going to be talking about in just a moment, which is known as the ABC Conjecture. And so Moser and Oesterlé were considering the Szpiro conjecture and asked, can we translate it into the realm of the integers? And they did, and that's how the ABC Conjecture came to be. In 1986, Ken Rivett was able to fill in the logical gaps, working on the work of Jean-Pierre Serre that filled in Frey's roadmap and made it rigorous. And after that, it was known that if the Taniyama-Shimura conjecture is true, but for a specific class of elliptic curves, which are known as semi-stable elliptic curves, then Formosas theorem would follow. And finally, in 1994, Andrew Wiles and Richard Taylor proved the Taniyama-Shimura conjecture for semi-stable elliptic curves, thereby ending the 357-year search for a proof of Formosas theorem. And so, for our discussion, we're going to come back to Formosas theorem as it's connected to the ABC conjecture, and we have seen some glimpses of elliptic curves already. So let's go ahead and continue towards the ABC conjecture. So first, I wanted to make a definition. We're going to take some positive integer n, and we're going to define the radical of n to be the product of all the distinct prime factors of n. So as an example, and as a convention, the radical of 1 is equal to 1. And so let's go ahead and consider the radical of 8 times 9. The distinct primes dividing 8 and 9 are 2 and 3, so the radical of 8 times 9 is simply 6. If we look at the radical of 17,640, it's just going to be equal to 2 times 3 times 5 times 7, since the prime factorization of 17,640 is as given here. And now we can state the ABC conjecture in its explicit form. And what it tells us is that if A, B, and C are relatively prime positive integers, such that A plus B is equal to C, then C is less than the radical of ABC quantity squared. Now, this conjecture is actually very powerful because from it we can prove Formosas theorem for exponent n greater than 5. Let's do that now. So the way we're going to go about the proof is by contradiction. So let us suppose that we have a counterexample to Formosas theorem for exponent n greater than 5. So that means that we have some a, b, and c integers where a times b times c is not equal to 0, and a to the n plus b to the n equals c to the n. Now to apply the explicit ABC conjecture, it is crucial that we satisfy the assumptions that the a, b, and c that we're looking at are relatively prime, but if we have such a counterexample to Formosas theorem, we can always reduce to the case where a to the n and b to the n and c to the n are relatively prime. And so let's go ahead and take that as our assumption. And so now, if we apply the explicit ABC conjecture to this equation here, what we get is that c to the n has to be less than the radical of a to the n times b to the n times c to the n quantity squared. But the radical is just the product of all the distinct primes dividing a to the n times b to the n times c to the n, and here n of course is greater than 5, and that's just going to be the same as the radical of just ABC, since we'll have the same exact prime factors, distinct prime factors. And so we have ABC here, but now quantity squared, and now we have to ask, what is the greatest possible value that this could ever be? Well, the radical of n the greatest possible value it can be is n, in the event that it's a square-free quantity. And so here we will get an inequality, and we're going to have that this is less than or equal to ABC quantity squared. But now, let's come back over here, and from this equation, since we know that a, b, and c are positive integers, we know that a to the n has to be strictly less than c to the n. And similarly, b to the n has to be strictly less than c to the n. Together, this implies that a has to be less than c and b has to be less than c. So now, we can come back to our inequality and replace a with c and b with c. But doing so gives us c cubed. And then that quantity squared, so we get c to the 6. But now we are done, because what we get is that now c to the n is strictly less than c to the 6, and that implies that n is less than 6. So then, n has to be less than or equal to 5, which is our contradiction. And we're done. We got Formosas theorem for exponent n greater than 5. But this is the explicit form, and this was first conjectured by Baker in 1995, but the actual ABC conjecture of Master and Oesterlé, what it states is that for every epsilon greater than 0, there are only finitely many relatively prime positive integers a, b, and c with a plus b equals c, such that the radical of a times b times c to the 1 plus epsilon is less than c. A question we could ask is it really necessary to have that epsilon is greater than 0? What happens if we take epsilon to be 0? And it turns out that there are infinitely many such positive integers a, b, and c that satisfy the radical of ABC is less than c. And so we're going to make a definition. So rather than say we have positive integers a, b, and c that are relatively prime, we're going to go ahead and simply say that we have an ABC triple. And so by an ABC triple, we mean a triple of integers a, b, c, where a, b, and c are relatively prime positive integers such that a plus b is equal to c. And then we're going to say that an ABC triple is good if the radical of ABC quantity squared is strictly less than c. And so this is the case where epsilon is equal to 0 in this inequality. Then we can show that the following ABC triple is good for every positive integer k, showing that epsilon greater than 0 is crucial in the statement of the ABC conjecture. So if you're curious on how one proves this, I'm going to go ahead and just give a quick sketch. Since we're trying to prove that it's good, it really suffices to show that 9 to the k minus the radical of 1 times 9 to the k minus 1 times 9 to the k is positive. And so if we show this, then we would be done, because that will tell us that then 9 to the k is greater than the radical. And that's exactly what it means to be good. And so working from here, we make the following observation, that this here is exactly the same as 9 to the k minus the radical of 9 to the k minus 1. But then the radical of 9 to the k, since the only prime dividing 9 to the k is going to be 3, we can just drop the 9 to the k and replace it with a 3, and that preserves the radical. But we can go further, because 9 to the k minus 1 and 3 are relatively prime, so we can actually take out 3 from inside the radical. And so this gives us 9 to the k minus 3 times the radical of 9 to the k minus 1. But now, let's look at 9 to the k minus 1. This is a difference of squares. And since it's a difference of squares, we have that it will always be divisible by 8. Alternatively, we can view this as follows. We can think about it from the perspective of modular arithmetic. 9 is congruent to 1 mod 8, so we're going to have 1 to the k minus 1 mod 8. But this is always congruent to 0 mod 8, so therefore this here is always going to be divisible by 8. And with that, we can go ahead, do 9 to the k minus 3, and then the radical of 9 to the k minus 1 is going to become the same as the radical of 9 to the k minus 1 over 4. Because upon dividing by 4, we are still going to have that the prime 2 dividing 9 to the k minus 1 over 4. And now we go back and do the same idea that we did in our justification for Formosas Theorem. This is the greatest value this can be is 9 to the k minus 1 over 4. And so now this will give us the inequality. 9 to the k minus 3 times 9 to the k minus 1 over 4. And then you can verify that this here, after expanding, will always be positive. And so that will show that this here is always a good positive ABC triple for each integer k. Now this result is actually a special case of a more general statement that tells us that if we have an odd prime p, then for each positive integer k, the following ABC triple is always good. And so what we just considered is the case where p was equal to 3, so we had 3 to the 3 minus 1, 2. And so that was how we got the 9 to the k minus 1. So the way that I got introduced to the ABC conjecture was by considering these types of questions. So back in 2010, I participated in the Mathematical Sciences Research Institute undergraduate program, MSRI Up. And our research advisor, Dr. Edric Owens, who would go on to be my doctoral advisor, introduced us to elliptic curves and the ABC conjecture, which was one of the research project I tackled for the summer. And so as an Easter egg, so here's a photo of that was taken in the first 2 weeks of the program, and our previous Lathisms lecture series speaker, Dr. Alexander Diaz-Lopez, is in the photo as well, so you can find him. And so as in the culmination of the summer, one of the results that my group and I that we proved was the following. And so this was joint work with Tillman and Watts. And so we showed that if we have a good ABC triple, A0, B0, C0, with A0 even, then for n greater than or equal to 1, we can define the following sequence of ABC triples recursively, where we let p sub n be 2 to the a sub n minus 1 times b sub n minus 1 quantity squared, and then we do that for the second term, and then here's the third term. And it turns out that this here is always a good ABC triple for each n. And so this was one of the results that we proved that summer, and the way that these quantities came were from elliptic curves. And so I worked on this in 2010, and then the material I'm going to talk about later actually came about from me revisiting that work back in 2017. I decided to look back at the work from MSRI Up, and that motivated and influenced the material that we're going to talk about in the section on elliptic curves and the modified Szpiro conjecture. But as we talk about good elliptic curves, one thing that we want to now look at is how do we go about comparing good ABC triples. And the way we go about that is by what is known as the quality of an ABC triple. And so what the quality of an ABC triple is the following. We take the logarithm of C over the logarithm of the radical of A times B times C. And in particular, we get that an ABC triple is good if and only if its quality is greater than 1. Because if we come back to the definition of a good ABC triple, we can take logarithms of both sides that will preserve the inequality. Dividing them by the logarithm of the radical of ABC on both sides will give us 1 is less than the logarithm of C over the logarithm of the radical of A times B times C. And with the quality, we can then do computational observations on ABC triples and get a handle for the validity of the ABC conjecture. So here are a few examples of qualities. So we go back to the first example with 1, 9 to the k minus 1, 9, and consider the case where k is equal to 1. That will give us the ABC triple 189. The quality of that is approximately 1.23. Had we let k be 2 in that example, we would have the ABC triple 1, 9 squared minus 1, 9 squared, and that quality will be approximately 1.29. But because we will have that this will always be a good ABC triple for every positive integer k, we can consider 1, 9 to the 100 minus 1, 9 to the 100. And then the quality there is 1.03. But the ABC conjecture tells us that there should be only finitely many ABC triples whose quality is greater than 1 plus epsilon in this new way of thinking about this. And so what we expect is that as we get larger and larger, these numbers should be tending closer and closer to 1 if the ABC conjecture is true. Here's a few more. If we go back over here and now consider the case when p is equal to 5, we will have 1, 5 to the 4th minus 1, 5 to the 4th. And the quality of that ABC triple is approximately 1.08. If we look at this the result from 2010, we can also plug in here the ABC triple 8, 1, 9. And so that satisfies the assumption 8 is even, 1 plus 8 equals 9. That is a good ABC triple. And we go ahead and consider then p sub 1. So we're plugging in a sub a naught will be 8, b naught will be 1. And so we go ahead, plug these in, and this will give us the resulting ABC triple here. And then the quality of that is 1.055 approximately. And so from 2006 through 2015, there was a network computing project that sought to find all good ABC triples with C less than 10 to the 18. And they did. They found all the good ABC triples with C less than 10 to the 18, and it was roughly around 14 million. And when the project ceased operation, they had actually found a total of 23.8 million good ABC triples, and this informs the computational evidence for the validity of the ABC conjecture. So specifically, they found of these 23.8 million good ABC triples, only 240 of them have quality at least 1.4. And the largest quality that they found is 1.6299, which corresponds to the ABC triple 2 plus 3 to the 10 times 109 equals 23 to the 5th. And so from the numerical evidence, if we go back to the explicit ABC conjecture, we had that C was less than the radical of A times B times C quantity squared. The computational evidence suggests that if this happens to be the largest quality for an ABC triple, then we can replace the exponent of 2 with 1.63. And actually I should note that in Baker's original formulation, the exponent was not 2, but rather 1.75. I chose it to be 2 just for the purpose of the example that we were doing for Formosas Theorem. But we can actually, if the computational evidence is true, we can drop that exponent further to 1.63. Moreover, we have the following graph that tells us essentially the quality in intervals for all the 23.8 million good ABC triples that were found by the ABC at Home project. So this graph is due to Barta Smith, and what it shows is the 148 unbeaten ABC triples. Now, what do we mean by an unbeaten ABC triple? What that means is we're going to be looking at the qualities of these triples, and so we're now on our x-axis we're graphing this log C. And so we're looking here between C being between 0 and some value between 10 to the 10, then the largest quality of an ABC triple occurring in that interval is the approximately 1.6299 that we just saw, and so that will occur here. The next largest ABC triple is going to be in this interval here would be just slightly smaller than that, and then we can continue, and as we can see, the largest qualities in the intervals continue to drop, and so we sort of have this logarithmic decay as we go further. And so from this point of view, we can now ask if it happens to be that this here holds, then we can take epsilon in the ABC conjecture to say be 0.2. The ABC conjecture states that there should be only finitely many good ABC triples having quality greater than 1 plus 1.2, since our epsilon is 0.2. And so we would have them, right? Then they will all, if it were the case that these are all of the ones that are here, so that after this point, there are no ABC triples having quality greater than 1.2, then all the finitely many will occur within C being less than 10 to the 100. And so as we go further and further, as our epsilon gets smaller, and as we go further and we let epsilon get smaller and smaller, then we should be able to then cut off. And then all the ones going over here will be the finitely many that we would find. So what are some consequences of the ABC conjecture? So we talked about Formosas Theorem in the case of the explicit ABC conjecture, but it turns out that the ABC conjecture actually implies Faultings Theorem, and this was shown by Elkies in 1991, and Gerd Faultings got the field medal for proving this. And what Faultings Theorem states is that if we have a curve of genus greater than 1, then it will have finitely many rational points. And the result is actually more general since it extends to number fields. And so some curve of genus greater than 1 over some number field will only have finitely many k rational points. Another result that is a consequence of the ABC conjecture concerns the square-free values that a polynomial with integer coefficients can take. So specifically, if we let f of x be a non-constant polynomial with integer coefficients, and let us suppose further that f of x does not have repeated roots, and that the largest positive integer dividing f of n for each integer n is 1. Then if the ABC conjecture is true, then there will be infinitely many integers n such that f of n is square-free. I should mention that we don't need to use the ABC conjecture in the case where the degree of the polynomial is equal to 2 or 1, and so in the one case will be automatic, the two case is due to Nagel in 1922, and in the n equals 3 case it was shown by Ergels in 1953. But the moment we're looking at a polynomial with degree greater than or equal to 4, one requires the ABC conjecture to state that there are infinitely many square-free values for such a polynomial. This result has also been generalized by Bjorn Poonen, and so it's extended towards polynomials with multiple variables. And so one more result, which we're going to come back and touch upon later, is this result of Brauken, Villaseta, Greaves, and Chinsel. And what they looked at is the set of all the qualities of ABC triples. And so they showed that if the ABC conjecture holds, then the set of limit points of the quality of ABC triples is going to be precisely 1/3, 1, including the endpoints. And so the 1 here, we actually already have shown that this is a limit point by virtue of having that there are infinitely many good ABC triples. So since there are infinitely many good ABC triples, if the ABC conjecture is true, then the lim supremum should be exactly 1. And so that will be the corresponding limit point here. So that concludes our discussion on the ABC conjecture, and so what I am going to do now is transition towards elliptic curves and give the necessary terminology to state the modified Szpiro conjecture to which the ABC conjecture is equivalent to. So we begin with the following loose definition for an elliptic curve. And so what we're going to be looking at is rational numbers a sub 1, a sub 2, a sub 3, a sub 4, and a sub 6. I'll mention why we skip a sub 5 in just a moment. But we want to look at this in the following configuration. We're going to be looking at the following implicit function, which we're going to call e. And so the reason for skipping a5 comes from complex analysis, where we can view x and y as having poles at infinity. And specifically, what we get is that the pole of y is going to be of order 3, and the pole of x is going to be of order 2. And so the indexing here is chosen so that 1 plus the pole of x plus the pole of y is equal to 6. And so that's how we get the labeling. So that's the reason for why a5 is missing. But now, once we have such an equation, we're going to define the following c4, c6 and discriminant. And please do not worry about the messy formulas that are here. What I want to emphasize is, given any equation of this form, we can always compute the c4 and c6 from those coefficients. And so we have these c4, c6, and then we can define delta, which will be the discriminant of e. And delta will simply be c4 cubed minus c6 squared equals, over 1728 is delta. And when we say that we have an elliptic curve, what we really mean is that we have this equation here with the property that its discriminant is non-zero. But we also require an additional point, which we call the point at infinity, which I'm here referencing as a scripto. Now, the reason for this point at infinity is that elliptic curves don't really live inside the plane, as we can graph it here, but rather they live in projective space. And so when we view it from the point of view of projective space, we do have that additional point that will not be a point on this graph. So let's look at a few visualizations. So we have here two curves, and one is an elliptic curve and the other is not. And so the red curve, y squared plus 2xy plus 3y equals x cubed plus 4x squared plus 5x plus 6. Now this here is an elliptic curve since its discriminant is non-zero. However, y squared equals x cubed plus x squared is not an elliptic curve since its discriminant is 0. And a way of interpreting discriminants is that it's measuring, if it's equal to 0, it's telling us that the equation when we look at the graph, we're going to have a double root or a triple root. And so here we have a double root for the curve at the origin. And so that's the reason for why this here is not an elliptic curve. We're going to now define the set of rational points on the elliptic curve, and so we're going to denote this by e of q. And so this set is specifically just the set of points x, y in the rational numbers, in the Cartesian product of the rationals with itself, that satisfy the equation here. But then we must also tag along the point at infinity. And we'll talk about more why we want to have that point at infinity in just a moment. But first, let us consider the following example. We have the elliptic curve y squared equals x cubed minus x. What are some points on e of q? Well, by definition, we already know that the point at infinity is just going to come along for the ride. But we can also see that x, y equals the origin is a solution. We also have that if we let x equals 1, then we have 1 minus 1 is equal to 0, so then 1, 0 is a solution. And in fact, it turns out that the only rational solutions to this curve are the origin and then plus or minus 1, 0, and that is it. And the reason for calling it the point at infinity and writing it in this notation is that it turns out that this here forms a group. And in 1922, Mordau actually proved that this set is always going to be a finally generated abelian group. And the point at infinity is its identity. So if we have an abelian group, that means that we can add 2 points on the elliptic curve. Like, how does that addition work? And so here's a visualization of this. If we start with 2 points on the curve, say P and Q, the way we add P and Q is that we'll draw a straight line passing through P and Q, and then that will intersect at a third point R. And then we can imagine that we're drawing a line from R to the point at infinity. And so we're just going off to the distance, and then we can imagine that we're intersecting that point at infinity off in the distance. But then along the way we also intersect the curve at another point, and that's the point we call p plus q. There's of course some special care that needs to be taken. What if we want to add p to itself? Well, in that case, the line that we would draw is just the tangent line at p. But then the geometric idea still holds. And so what I'm interested in is a specific subgroup of the rational points on the elliptic curve, which are the ones of finite order. And so I'm going to introduce some terminology from abstract algebra. So for every positive integer n, let us denote C sub n to be the finite cyclic group of n elements under addition. If you have not seen abstract algebra, one way of viewing this is if we have C sub 6, then it's going to be the set of numbers 0, 1, 2, 3, 4, 5. And the way that we define addition is by modular arithmetic modulo 6. In other words, we're adding numbers and then looking at the remainders after dividing by 6. So we add 5 plus 5, it will be equal to 10. But then we divide by 6, the remainder is 4, so 4 is going to be the sum of 5 plus 5 inside C sub 6. But one thing to note is that if we take any of these quantities and we add them to themselves 6 times, then we will always come back to 0. So of course 0 times 6 is 0, 1 times 6 is 6, 2 times 6, and so by definition we will always have that all of these will be divisible by 6, so the remainder will be 0. And so that's one of the main things you want to keep in mind, is that in here we just have to add, if we take any of these quantities, add them to themselves a number of times, we will eventually get back to 0, which is the identity of this group. And so when we're looking at the rational points on the elliptic curve, I want to consider the subgroup of all the points that have finite order, all the ones that we can add to themselves over and over again and eventually get to the point at infinity. And so this is what we call the torsion subgroup of an elliptic curve, and so we're going to denote this by EQ tors. A celebrated result of Barry-Mazur from 1977 tells us that if we have an elliptic curve over the rational numbers, then there are exactly 15 possibilities for what the torsion subgroup can be, and they are given as follows. It could be the cyclic group of order n, well, isomorphic to the cyclic group of order n, where n is between 1 and 10, including the boundaries, and then we skip 11 and we go to 12. And I'll mention a comment later on why 11 is missing here. But we also have another possibility. It could be the Cartesian product of two cyclic groups. So specifically we will have the cyclic group of order 2, Cartesian product, the cyclic group of order 2n, where n is now between 1 and 4. And the example that we just considered, we saw that it has 4 rational points. It turns out that this group is actually isomorphic to 2 copies of the cyclic group of order 2, just taking the Cartesian product of them. And specifically, it is generated by the origin and negative 1, 0. Or you could choose 1, 0 as well, will still give you the same group. So we have a group structure, so then we can talk about when are elliptic curves isomorphic to themselves. And so we have to be a bit careful because we want to specifically talk about isomorphisms over the rational numbers. 2 elliptic curves can be isomorphic, but not necessarily over the rationals. And so I want to look at what are known as Q-isomorphic elliptic curves. And so here is an illustration. So there are 3 curves given here, and they are all isomorphic. But notice that they are all essentially scales of the others. And so that is one way of perceiving it. I'm going to go ahead and give you another depiction. So here's a visual demonstration of how isomorphic elliptic curves look like. So in this example, we have that P1 is a point on the curve, and then it's chosen in such a way that if we add P1 plus P1, then we will get back the point P2. And if we add P1 to itself 3 times, we'll get P3, add P1 to itself 4 times, we'll get P4, and finally if we add P1 to itself 5 times, we'll get back the point at infinity. So in other words, the torsion subgroup of this elliptic curve contains the cyclic group of order 5 as a subgroup. And so here is how we can view isomorphisms. So if we translate the curve, it will preserve the geometry. And so all of those curves will be isomorphic. So for example, we can do vertical translations. We can also do horizontal translations. We can do scaling. And so let me just zoom out so we can like scale the curve. So here it's a bit larger. We can then make it smaller, but all these curves are isomorphic. There is also another type of isomorphism which comes from essentially a rotation that preserves the group structure. And so here's what I mean by this. So we can rotate this, but notice how all the points are there. And if you go up and consider this curve here, and then do P1 plus P1, it will still equal now the P2 of this new curve, so on and so forth. And so that's one way of visualizing Q-isomorphic elliptic curves. But the main takeaway is that every time that we do these sort of movements to consider different isomorphisms, like if we look at this curve here, the discriminant of this curve will be different than the one we just had. And the discriminant of this curve will be different than, say, this one right here. And so the discriminants do change, but they do change in a very nice manner. So now we're going to define what we mean by a global minimum model. So by a global minimum model of an elliptic curve E, we mean an elliptic curve given by an equation of this form, which we are going to now refer to as a Weierstrass model. And it has the property that all the coefficients occurring are integers, as opposed to rational numbers as we first defined them. And if we consider all the Q-isomorphic elliptic curves to this global minimum model, then its discriminant in absolute value will be the smallest over all the Q-isomorphic elliptic curves. So in other words, all the translations, scalings, as well as those rotations we just saw, we will have that the curve has its absolute value, and absolute value is the smallest possible. And we call that discriminant the minimal discriminant of an elliptic curve. And so more precisely, we say that the minimal discriminant of an elliptic curve E is the minimal discriminant associated to a global minimum model. And now, going forward, we're going to be concentrating on the minimal discriminant and then the associated C4 and C6 attached to a global minimum model of a curve. Next, we will define what it means to be a conductor, but I'm going to give a very hand-wavy definition. And so the conductor of an elliptic curve is roughly the product of all the primes dividing the minimal discriminant. And then we have those primes raised to some exponent f sub p, where f sub p is at least 1. And so I say hand-wavy because I am not defining what this f sub p is, but I will mention that this comes from, one can compute this using Tate's algorithm. And so we call these f sub p's the local conductor exponent. And it turns out that if fp is greater than 1, then we have that the prime p divides the greatest common divisor of the minimal discriminant and then the associated C4 to a global minimum model. When this is the case, we say that the elliptic curve has additive reduction at that prime p. If f sub p, if we have that all the local conductor exponents are at most 1 for every prime p, then we will say that the elliptic curve is semi-stable, and now this harkens back to when we were discussing the history of Formosas Theorem. What Andrew Wiles and Richard Taylor proved was that the Taniyama-Shimura conjecture was true for all elliptic curves that are semi-stable. So in other words, all elliptic curves whose conductor exponent, when we look at them, is at most 1. And one thing to note is that if we have a semi-stable elliptic curve, then because the exponent, the local conductor exponent is at most 1, we have that the conductor will be equal to the radical of the minimal discriminant of E. So let's do a quick example just to get familiar with these terms. So we have this elliptic curve here. Its minimal discriminant and C4 and C6 are given below. So we have our quantities. Notice that all the primes of the minimal discriminant C4, the only one that they share in common is 2. So by this statement, we now have that this curve has additive reduction at 2, and so the local conductor exponent is going to be greater than 1. For the other ones, for the other primes appearing in the minimal discriminant, they will also occur in the conductor, but just raised to the 1 power. And so specifically, we have that the conductor of this curve E is this quantity right here, where f sub 2 is the local conductor exponent at 2, and we know it's at least 2, since we have additive reduction, and in fact, it is the case that the local conductor exponent there is 4. And so now we have all the necessary language to finally state the Szpiro conjecture of 1981 which motivated both the ABC conjecture definition formulation as well as the investigation into Formosas Theorem. And so what it states is that for each epsilon greater than 0, there are only finitely many non-isomorphic rational elliptic curves E such that the conductor raised to the 6 plus epsilon is less than the absolute value of the minimal discriminant. Fast forward to 1988, and Oesterlé proved that the ABC conjecture is equivalent to the modified Szpiro conjecture, which states for each epsilon greater than 0, there are only finitely many rational elliptic curves, and so specifically non-isomorphic rational elliptic curves, such that the conductor to a 6 plus epsilon is less than the maximum of the C4 cubed, comma C6 squared, where now the C4 and C6 are associated to a global minimum model. Now, that means that in order to understand the modified Szpiro conjecture, we need to be able to compute a global minimum model for an elliptic curve, as well as the conductor of an elliptic curve. And so those are the main ingredients for understanding the modified Szpiro conjecture, and the Szpiro conjecture for that matter. One observation is that notice the similarity with the ABC conjecture. As we saw, if the curve is semi-stable, then the conductor is equal to the radical of the minimal discriminant. And so here, the conductor is really taking the role in the ABC conjecture of the radical of A times B plus C. And then the maximum is taking the role of the C. And so we have this dictionary now. And so we could ask, what if epsilon is equal to 0? Can we do the same exact things that we did in the context of the ABC conjecture? And the answer is yes. We get the following definition. So by a good elliptic curve, we mean an elliptic curve whose conductor raised to the 6th power is less than the maximum of C4 cubed, comma C6 squared. Now, we can ask this as with good ABC triples. Are there infinitely many good elliptic curves? And the answer is yes. So this was first shown by Moser in 1990, and he showed that there are infinitely many good Frey curves. Now, we have not discussed what Frey curves are, but they are the same elliptic curves that Gerhard Frey used back in 1982 through 1985 to make the connection between the Taniyama-Shimura conjecture and Formosas Theorem, and so they are named in his honor. One of the important properties of the Frey curve that lend themselves well for both the study of the Szpiro conjecture and modified Szpiro is that they come equipped with a easily computable minimal discriminant and conductor. And as a consequence, Moser was able to use this family to prove that there are infinitely many good elliptic curves. But now, this result was non-constructive. And so in 2017, I revisited the material that I had done in MSRI Up, and along the way I came across Moser's result, and I asked him, we prove this constructively. And so with my knowledge on endophantic geometry, I decided to give that an attempt, and I succeeded in proving Moser's theorem constructively. But then I wanted to generalize it. And so one thing about the Frey curve is that in their torsion subgroup, they always contain the Cartesian product of the cyclic group of order 2 with itself. And so they do have a torsion subgroup that is non-trivial. And so I proved a generalization that says that if now T is one of the 15 torsion subgroups that we mentioned earlier from Barry-Mazur's theorem, then there are infinitely many good elliptic curves E whose torsion subgroup is isomorphic to one of those 15 T's. And this proof is constructive. And so it leads us to have sequences of good elliptic curves akin to what we saw with the good ABC triples. So for example, the following curve E sub k, where now k here is some positive integer, given, and then we have the equation given here. This here is going to be a good elliptic curve for every single positive integer k, and moreover, the torsion subgroup of this elliptic curve is isomorphic to the cyclic group of order 5. And then similar results are found in the paper for the other remaining torsion, the other 14 torsion subgroups. Now this result allows us to then consider analogs of what the ABC at Home project did in terms of computationally understanding the ABC conjecture. And so to this end, let me define what the naive height of an elliptic curve is. The naive height is simply the following quantity, 1 over 12 times the logarithm of the maximum of C4 cubed, C6 squared. C4 is an absolute value, of course. And again, C4, C6 here are associated to a global minimal discriminant. Now, one thing about the naive height that I want to point out is that if we fix some positive real number L and we ask how many elliptic curves are there whose naive height is at most L, then there will always be finitely many. And so that's one way of thinking about naive height, is that if we want to talk about a collection of elliptic curves up to a certain value, then we can now investigate this naive height. Similarly, we can define the modified Szpiro ratio, sigma sub n, which is the analog of the quality of an ABC triple. And so this is going to be the logarithm of the maximum of the absolute value of C4 cubed, comma C6 squared, over logarithm of the conductor. And equivalently, we get that an elliptic curve is good if and only if the modified Szpiro ratio of the curve is greater than 6. And so the constructive nature of the proof that I just mentioned allows us to then construct a database that mirrors the ABC at Home project. And so specifically, I have constructed a database that consists of roughly 14 million good elliptic curves. And with such a database, we can give an explicit modified Szpiro conjecture akin to the explicit ABC conjecture that we had at the start. So for example, from the database, one thing that comes out is that if we are considering elliptic curves whose torsion subgroup is isomorphic to C2 cross C8, then the computational evidence suggests that the maximum of C4 cubed in absolute value, comma C6 squared, is going to always be, at most, the conductor raised to the 7.35. And so here is a histogram showing how the modified Szpiro ratios of elliptic curves in this database of approximately 14 million curves looks like. And so what we see is that we would expect, as we saw with the quality, we should expect that a good chunk of them all gravitate closer to 6. And getting further away from 6, we expect them to be rare. In the same way that we saw the following graph due to Barthes-Smith pertaining to good ABC triples and their qualities, we can look at something similar in the context of the modified Szpiro ratio. So for instance, if we take all elliptic curves in set database and we order them by their naive height, then we can look at the largest modified Szpiro ratios occurring in this database. And what we see is that the largest modified Szpiro ratio is just over 16. But as we get past naive height 20, the largest modified Szpiro ratios occurring after that are all going to be less than 8. If we go past naive height 30, then the greatest modified Szpiro ratios that we see are below 7. And as we go further and further out, we have that the modified Szpiro ratios are tending closer and closer to 6, as we would expect if the modified Szpiro conjecture is true. And so this database does give us some evidence for the validity of the modified Szpiro conjecture from a computational point of view. And so to conclude the talk, I want to transition now to talk about modular curves, which serve as the backbone for proving that there are infinitely many elliptic curves that are good with a specified torsion subgroup, as we just mentioned. And so in order to discuss modular curves, I want to harken back to our discussion of Diophantus's classification of Pythagorean triples. After we had Diophantus's result, we reformulated it in terms of equivalence classes, and we saw that for every rational number, we would have a corresponding equivalence class, which corresponded also to Pythagorean triples. In the same manner, we arrive at modular curves, and so these are curves whose points correspond to isomorphism classes of pairs E, P, where E is an elliptic curve and P is a torsion point of order n, and so this will correspond to the points on x1 of n, where n is a positive integer greater than 1. So what do we mean by isomorphism classes of pairs and that they are equivalent? And so what we mean is that two pairs E, P and E prime, P prime will be equivalent if E and E prime are Q-isomorphic. And so if we let phi denote the isomorphism between E and E prime, then phi of P will be sent to P prime. And so phi of P equals P prime. So here is a visual depiction. So we have here three elements in the same isomorphism class of pairs, E, P. And so all the red, green, and blue curve here, they are all isomorphic over Q. But the isomorphisms corresponding to them will all send their corresponding P to then the P double prime or P prime respectively. And intuitively, one way of seeing it also is we have our curves, they're all isomorphic, and in this case they're all scaled versions of the other, and we see that the points in question are all occurring in this around the same spot for each curve. So P is up here, but it's also occurring up here for the green curve and the blue curve at the very top. In 1976, Coover wrote a table that gave all the parameterizations for the genus 0 modular curves, and there are exactly 15 of them, which coincides, of course, with the 15 torsion subgroups which Mazur gave in his famed proof from 1977. And so this allows us to essentially understand all curves that have a non-trivial torsion point. But before we proceed, I want to just come back to something I mentioned earlier. So when we first saw Mazur's torsion theorem, I mentioned that we skip 11. But why? We can view this from the point of view of modular curves, because the corresponding curve is x1 of 11. It's the curve that parameterizes elliptic curves over Q, or more generally number fields, with a point of order 11. And it turns out that x1 of 11 has genus 1. Therefore, it is an elliptic curve. So it's an elliptic curve whose points are elliptic curves with points of order 11. And the group of rational points on x1 of 11 over the rational numbers is isomorphic to the cyclic group of order 5. But the 4 non-identity points all correspond to curves whose discriminants are equal to 0. We call these cuspidal points. And so the reason why we have no curve over Q having a torsion point of order 11 is because x1 of 11 has no non-cuspidal points over Q. So with that, let's continue back with Couvert. So Couvert had these parameterizations, but then Ono, Xu, and Sang also studied further cases in the case when there's a 2 torsion point involved, since things do get a bit complicated. The corresponding modular curves are what are known as coarse moduli spaces. And so, building on their work in my thesis, I studied 15 different parameterized families of elliptic curves, which I labeled E sub t, and they have the property that t embeds into the torsion subgroup of this family. But more importantly, they parameterize all rational elliptic curves with a non-trivial torsion point. So in order to understand curves with a non-trivial torsion point, it suffices to understand how these parameterized families of elliptic curves behave. And so here is a table giving the actual equations for these 15 families of elliptic curves. Although I left C2 cross C8 since it was overflowing from the slide. And so here, A and B, we are interpreting them as being integers that are relatively prime, and you'll see that some of these have a d involved, and that will correspond to a square-free positive integer. In the case when we look at the cyclic group of order 5, this actually is coming from what is known as the universal elliptic curve over the modular curve x1 of 5. And I'm going to now give you a visual depiction of how that that universal elliptic curve looks like. So we come back to our earlier depiction, but instead of considering Q isomorphism classes, what I am going to be doing now is showing how we get different elliptic curves, each having a torsion point of order 5. And all that I have to do is just change this slider here, labeled H. And the way you want to think about this is the analogy between the Pythagorean triples. As I switch the slider, I will get back a different isomorphism class of pairs of curves. And so, for example, I change this slider, and you'll see that we are actually getting non-isomorphic elliptic curves as we vary the slider over in this case, the rational numbers. And so let me just come down to the negative rationals we have here. And so all of these correspond to non-isomorphic curves, each having a torsion point of order 5, and that is consistent with this P1. In my thesis, what I did was study each of these families and improve analogs for the Frey curve. In fact, the Frey curve is a special case of the family corresponding to C2 cross C2. And so more specifically, what I proved was that there are necessary and sufficient conditions on the parameters of each of these families E sub t, and so the parameters here are the A, B, and D. And these conditions allow us to determine the minimal discriminant, as well as the primes for when additive reduction happens, and we can also find sufficient conditions to determine a global minimum model. So in other words, this gives us an explicit classification of the minimal discriminant of all elliptic curves over Q that have a non-trivial torsion point. And that's just halfway there to understanding the modified Szpiro conjecture. Now, all that remains is understanding the local conductor exponent, but thankfully we have also classified that portion. And so this is in joint work with Manami Roy. And so we were able to show that for every prime for when the family E sub t has additive reduction, there are necessary and sufficient conditions on the parameters to find what is known as the Calera-Nearon type at the prime p, the local conductor exponent at p, as well as the local Tamagawa number at p. And the local Tamagawa number is one of the quantities that occurs in the famed Burton-Swinnerton-Dyer conjecture. But for our purposes, the main thing that we're going to focus on is the local conductor exponent. And so this now gives us some tools to investigate the modified Szpiro conjecture further. And so I'm going to go back to a result that we discussed earlier when we were talking about consequences of the ABC conjecture, namely Brauken, Villasetta, Greaves, and Schinzel's result, which said that if we assume the ABC conjecture, then the set of limit points of the quality is going to be precisely 1/3, 1. We're going to focus on a weaker question. What if we replace the quality with a modified Szpiro ratio of elliptic curves? What is the lowest possible value occurring in the set? In terms of like the limit points, what's the lowest possible value? What's the greatest one? The greatest one we already get from the fact that there are infinitely many good elliptic curves for each torsion subgroup. So 6 is the upper bound if the ABC conjecture holds. But the lower bound, we can actually now show using the classification of minimal discriminants as well as the conductor exponents. And so specifically, I have proven that if E is a rational elliptic curve that has T in its torsion subgroup, so where here T is one of the 15 possibilities from Mazur's torsion theorem, then there is a rational number L sub t that only depends on the torsion structure of the curve, such that the modified Szpiro ratio of E is always going to be greater than L sub t. And if we assume the ABC conjecture, then these lower bounds are actually sharp. And the reason for needing the ABC conjecture in the proof is that it requires Granville's result that if we have some polynomial with integer coefficients, then it takes upon infinitely many square-free values. And so the result is as follows. If the torsion subgroup is C2 cross C8, then the modified Szpiro ratio is going to always be greater than 4.8. If we have, say, a torsion subgroup of C4 for E, then its modified Szpiro ratio will always be greater than 2.4. An automatic corollary of this is that if the curve has modified Szpiro ratio that is strictly less than 1.5, or actually less than or equal to 1.5, then the curve must automatically have a trivial torsion subgroup. And we can actually go further and make now a conjecture in the same vein as the result of Brauken, Villasetta, Greaves, and Schinzel. And so specifically, we need some terminology to avoid considering isomorphic elliptic curves. And so what we are going to do is consider E sub q to be the set of all q isomorphism classes of elliptic curves. And we're going to let bracket E denote a q isomorphism class of E. Then we can extend the modified Szpiro ratio to values on the set of q isomorphism classes of elliptic curves by simply taking sigma m of the equivalence class of E to just be sigma m of E. And this is well defined since the modified Szpiro ratio depends on the conductor and the minimal discriminant, which are unique for all curves in the same equivalence class. And so with that, we can make the following conjecture, that if T is one of the 15 torsion subgroups allowed by Mazur's result, then if the ABC conjecture holds, then the interval L sub t, 6 is the set of limit points of the set corresponding to the modified Szpiro ratios of the isomorphism class of E, where now E has torsion subgroup T. And with that, that concludes my talk. Thank you so much for your time and for listening. Here are some references that occurred during the talk. If you're interested in learning more about the ABC conjecture, as well as its various statements and consequences over the integers, I highly recommend reading Martin and Miao's ABC triples paper, which is a great survey article on the ABC conjecture.